So let us look at now what are the different types of bond failure. And we can do direct, either the bar can pull out if the bond bearing mechanism is not adequate, or if you're using a very smooth bar and your embedment length in the concrete is very less, then when you pull on the bar, then the bar can just directly come out of the concrete. So, but however, for sufficiently confined bar, okay, that means you have adequate bearing, and if you're having some transverse reinforcement also, that is going to confine the concrete, then first, initially, the adhesive bond and friction will be overcome. That means it will go to zero as the bar force is increased. But then concrete will eventually crushes locally ahead of the bar deformation and bar pull-out results. Okay, that means the bearing, because the bearing, then concrete surrounding that rib area, it will be subjected to high level of bearing stresses. Then the concrete can crush locally, and the bar pull out. If the crushing is happening at all the rib location, the finally the bar will pull out. Okay. When the pull out resistance is overcome, or when the splitting is spread all the way to the end of the unanchored bar, the complete bond failure occurs. Okay. It happens in a progressive way. And splitting also occurs when small diameters are used with sufficiently large cover distance and bar spacing. So then you end up with this, because of local crushing, you will have splitting failure that is coming. And then finally you will have. Now let us look at the splitting of the concrete along the bar when this is going to happen. Okay. And when your cover or bar spacing is insufficient to resist lateral concrete tension resulting from the wedge effect of the bar deformation, that's what we talked about. The rib is going to act like a wedge, and it is going to create radial stresses that is going to create lateral concrete tension. And if your cover is very, very less, then you can have either this kind of a splitting, okay, right? Or you can have this kind of horizontal splitting, okay, which will run along the horizontal plane. This is a vertical splitting, okay. These both the splittings are possible. So this is your vertical splitting, okay. So this vertical splitting will happen when your bottom cover CB is less than your side cover. So this is your side cover. This is your bottom cover. So when your bottom cover is less than side cover, you tend to have this kind of a vertical splitting. Now, if your bottom cover is much higher than that of your side cover, then because of this radial forces, you will develop lateral splitting stresses, tensile stresses. Then, because I am having side cover less than the bottom cover, the splitting can happen in the horizontal direction like this, right? So splitting comes from wedging action when the ribs of the deformed bars bear against the concrete. That's what we discussed. So splitting can happen in the vertical plane like this, okay, or splitting can happen in the horizontal plane like this, right? So frequently this begins with the horizontal splitting usually happens when you have a diagonal crack that is forming because of the shear, or maybe a flexure shear crack that is forming in connection with the dowel action. And in fact, most of the time, shear and bond failures are often interrelated. When you have a shear crack or a flexure shear crack, and if your cover and your bond stresses are not adequately developed, then you have this kind of a horizontal plane splitting. Okay. Now, let us look at what is an ultimate bond strength and what is a development. Now, local bond failure, okay. So as we have seen, in and out bond stresses, okay. So there's going to be a large local variation of your bond stress can be caused by flexural and diagonal cracks very close to that other. We have seen that the bond stress will be maximum just adjacent to the crack, right? So when you have significant amount of flexural and diagonal cracking, you will have a large variation in your bond stress immediately adjacent to cracks, and then it can create a local bond failure. Okay, and usually this local bond failure, we need not be concerned if it is not propagating along the length of your bar. So, and this results in small slip and some widening of cracks and increase of deflections. However, it can be considered harmless if the failure does not propagate along the bar. So the local variations in the bond stress is generally not a concern. Okay, and we can tackle this also by providing end anchorages, hooks, or extended length of straight bar that we call that as development length. That means we will see what is development length. It is the length of the bar that is required to develop a particular tensile stress at the cross section where you want the stress to be developed. Okay, now let us look at what is development length. I have taken a simple case of a cantilever beam like this. Okay, and we know for cantilever subjected to load, you're going to develop tension at the top. So you put reinforcement like this, right? And let's look at this section CD. Okay, between C and D. Now, if you look at between C and D, and we know that here I'm going to develop a maximum bending moment. So at D, I'm going to develop a large tension force on the bar. Okay, that force, let's say it is equal to area of the bar times the stress in the bar for the particular bending moment. And let's say if it is W and L, we know the bending moment at that section is going to be WL square by 2. So for WL square by 2, I'm going to develop this tension force of, let's say, AB into Fs, and the stress is going to be Fs. Now, and we know that at this location 0, and I have developed tension force of this. So this difference in tension has to be accounted by the bond stress that are going to develop. Now the bond stress initially will be 0 and it will keep on increasing like this. So that is how the variation of the bond stress is kept like this. Okay, it is going to increase in a non-linear fashion, and you're going to have a maximum bond stress at the location at D, where you're going to develop this maximum tension. Right. Now, for calculations, what we do is we try to average them, and this variation is averaged and written as an average bond stress. So everything, though it is varying from 0 to tension, 0 to maximum value at the other end, we try to average them because a lot of local variations are going to be there. So we're going to use average bond stress in our calculations. Right. Now, what is development? Development length is the length of embedment necessary to develop full tensile strength of bar. Now, for example, in this stress Fs becomes Fy, that means I am achieving the yielding of the bar, then only I am effectively utilizing the material. Right? So, for example, for a section at for Fs at section, let's say here, so this is a section that I'm considering, or at let's say at D, okay, the tension force is AB into Fs, right? So maximum moment is at support. Now, what is the concept? The total tension force must be transferred from the bar to the concrete in a distant gel by bond stress on the surface. So that means to develop this force tension force equal to area of the bar times the yield stress. For design, we take 0.87 Fy. So let's say area of the bar multiplied by 0.87 Fy. What is the bond stress developed within that particular length to that? So I need to embed this bar to a certain length because the bond strength is a property. It is a design value will given to you depending upon what kind of material that you use, right? So strength, this average bond stress will be code will give you IS 456 will give you what is that we need to use it. So to satisfy this tension force, what we need to do, we need to provide this length, minimum length, so that this average bond stress multiplied by this length will equal to the tension force what I need to develop, right? So in other words, the development length is the length of embedment necessary to develop the full tensile strength of the bar, controlled by either pull out or splitting. Okay, so to develop fully develop the bar, I need to develop this tension force of area of bar multiplied by Fi, right? So and bond strength usually is given in the code, and we need to embed the bar for a certain length to achieve that full stress. Okay. Now let us look at how to calculate that. Okay. Now what is the tension force? Area of the bar multiplied by the stress, right? That should be equal to pi into diameter is your perimeter and length of embedment is L. So that gives me the total surface of contact, and I multiplied by average stress should be equal to the tension force, because if you look at it, 0 here and tension force is this, right? So 0 to tension force has to be developed by this average bond stress, right? Okay. So this average bond stress is acting over the perimeter over the length of L, right? So perimeter multiplied by length gives me the surface area over the bond it is bond stress is acting. So surface area multiplied by bond stress gives me the total bond force that is developed, that should be equal to your tension force maximum what I need to achieve, right? So in this way, I can develop an expression for an average bond stress as diameter. If you do simplification, you get diameter multiplied by stress divided by 4L, right? So the expression that is given in the code for development length is, now when I put LD on the other side, it will become diameter multiplied by stress divided by 4 times tau BD. But tau BD is your design bond stress that is specified by the code. Okay, tau BD is nothing but your bond, it is the design bond stress that has to be calculated. Now, what are the tau BD values that are specified by the code? People have done a lot of testing, and depending upon the grade of concrete that is used, because again, it is controlled by splitting failure, and splitting is controlled by tensile strength of the concrete. So, if higher the strength of the concrete, higher will be the tensile strength, and higher will be your bond strength, right? So, that is the reason if you look at it, it keeps on increasing the tau BD value as the grade of concrete is increasing. Now, they have limited for up to M4, M40 in your AS456. If more data is available, then it can be the tau BD values can be established for high strength concrete also. Now these are valid for smooth bars. Okay. Now nowadays we are using all deformed bars. So on deformed bars, we know that because of the wedge action, it can develop much higher bond stress, right? So these values have to be amplified by some factor. So that is what the code is going to give. It can be increased by 60 percentage for deformed bars. That is what we are nowadays using, and a further increase of 25 percentage of bars in compression. Now, why is it again bond stress is increased in compression? In compression, there are no cracks, right? In addition to that, I can develop bond by bearing. The bar can bear against the surrounding end bearing. Then also you can develop more bond stresses. So that is the reason the bond stresses are in tension for deformed bars. Whatever these values that are given in the table, class 26.211 can be increased by 60%. So that means I can multiply this by 1.6. And if I'm doing it for bars in compression, again this value can be multiplied by another 25%. That means development length, when we calculate for compression, it will work out to be 25% lesser than what you get for tension, right? So that is the idea. Now, again, development length we have discussed. Higher the tensile strength of the concrete, lesser will be your development length. And cover also, if you put large cover, then you can delay the splitting, so then it is better. And bar spacing also, if all of them are closely spaced, then your splitting stresses can overlap and it can create to easy splitting. So you need to have sufficient spacing. And if you have lateral reinforcement that is going to confine, so that this vertical splitting and horizontal splitting can be avoided, that's going to be better. Then also the bar location related to the beam depth, where it is there. Okay. And nowadays for corrosion resistance, people are also using this epoxy coating. Okay. So when you do this kind of epoxy coating, then the friction and adhesion is expected to be lesser. So that also we need to be accounted for. And also, if you're putting more reinforcement than actually what is required, then you will develop only less stress. Then also your development length can be appropriately reduced. Again, bar diameter. For the same tension force, instead of providing larger diameter, if I'm providing more number of small diameter, then you have more perimeter, then your bond strength, what you can develop is going to be much higher. So it is always a good practice to put smaller diameter of bars to achieve the tension force. Of course, you have to satisfy the detailing requirements as well. Right. Now let's look at what are the tests that we usually do for assessing the bond strength. So what we do is the basic simple test is this pull-out test. What we do is in a concrete cylinder, we embed the bar, okay, and then they will be the protruded bar will be put in UTM. You apply a tension force. Now you also need to create some reaction like this to hold this concrete cylinder so that it doesn't move, and you have to develop reaction. So you keep pulling and you find out at what load it is actually failing. So then you know your embedment length, you know the force tension force, right? So I can calculate now what is the bond stress because I know the surface area. Now L multiplied by the pi d is your surface area, and that area multiplied by the bond stress should be equal to the tension force at which it is failing. So now that I know the tension force when I do testing at which it is failing, I can calculate what is the bond stress that the particular bar can develop. Right? This is one way of doing it. It's a very simple test. But however, this does not really reflect the bar behavior in tension that happens in a beam. So when you have a bar in the tension zone, you know that you're going to have a lot of cracks. In this case, in this test, you're not going to have any cracks. Okay, everything is in compression. So there's going to be an additional confinement for the surrounding concrete because you're holding it for reaction. So whatever the result that we get may not actually replicate the real scenario that happens in flexural beam. So for that, another test was done, which is called as modified cantilever test. So here also what we do is we embed the bar and then we create some small sheet, or we make sure that at the end there is no contact, and so that this becomes your test region. And depending upon what kind of force that you apply, then you can find out what is the, if you start pulling it, of course you have to apply some reactions here to keep it in equilibrium. Then at what force it is failing, we know P. So this is basically like a cantilever, modified cantilever test. So this, when you do it, you can have cracks like this. So that is going to relate the real world scenario. Then the bond strength calculated from this test will be the actual closer to the real world, what happens in flexural. Now, okay, these are the things that we have discussed. What are the mechanisms of bond resistance, and then how the failure modes are happening. Now, let us look at how the IS 456 provisions are there for bond development. Okay, so flexural bond, we have seen that locally, you're going to have variations because of a change in your tension force in the bar or change in your shear. You know that the average bond stress is proportional to the shear that is acting. But these local bond stresses, as we have discussed, it's not really going to create. They are usually harmless if adequately designed. So that's why the concept in limit state design for flexural bond has shifted from control of local bond stresses and whose predicted values are anyway unrealistic in a pull-out test, and to the development of required bar stresses through provision of adequate anchorages. That means if I'm able to provide adequate anchorages and development lengths or at cutoff points, the cutoff point is we also cut the bars, because depending upon the bending moment variations, you can also cut the bars, right, where it is not really required. So, but you cannot cut it immediately. You have to cut it or extend it by a certain length to develop the forces what you need for the bending moment. So, in nutshell, so the flexural bond is taken care by making sure that the development length is adequately considered and proper anchorage for the bars are provided, right? So let's look at now. So that's what the development or anchorage bond we say it. So the computed stresses at every section of reinforcing bar, whether in tension or compression, must be developed on both sides of the section. So that means if I need certain tension force for a particular bar, and what is the maximum tension force I should be able to develop? Ideally, it should be at critical section, it should be yielding. But depending upon the bending moment profile, if I want to develop a particular tensile stress for the demand, I should be able to develop. If I don't have enough development length, I will not be able to develop that particular stress. So that is what it's saying. We should be able to develop the stress required on both sides of the section. So bending moment can be left and right. So both sides of the section by providing adequate development length, right? So if your straight bars are not able to provide that kind of stress required for demand, then what we can do is we can provide these kind of bends. Okay, and these are basically standard 90-degree bend, and this is basically standard U-type hook. So this standard U-type hook is this. So when you provide this kind of hooks, I can take equivalent anchorage of 8 times the diameter of the bar for a 90-degree bend. For a U hook, U type hook, I can take an equivalent anchorage length of 16 times diameter of the bar. So in addition to your straight portion, I can also add 16 times diameter. So in that way, especially when you're trying to develop this anchorages in column regions where you have a limited width, or in a wall when it is embedded into a shear wall, then the space may not be adequate. to develop that particular stress. Then we resort to providing these kind of bends or hooks. Sometimes we also put, we weld a plate, welded bar also we put.